2 episodes after we started, we taught text to become numbers. Back when we tokenized a sentence into input IDs, we turned words the model could not read into integers it could. Audio is the same trick, wearing a different coat. A microphone gives you a waveform, a long list of air pressure numbers wiggling thousands of times a second, and a model can no more hear that than it could read raw text. So Whisper, OpenAI's speech model that lives on the hub, ships with its own feature extractor, the audio equivalent of a tokenizer. It chops the waveform into a spectrogram, the exact kind of numeric input the encoder expects. Same idea as episode 2. Take messy human signal, hand back clean model input. Today we feed it a 5-word clip and get the sentence back, perfectly spelled. Speech recognition used to be a graveyard of brittle pipelines. Phoneme dictionaries, hand-tuned acoustic models, language models bolted on the side, each one a place to go wrong. Whisper collapses all of that into a single sequence-to-sequence transformer, trained on 680,000 hours of audio scraped from the web. You give it sound, it gives you text. No dictionary, no alignment model, no glue. The whole stack we're about to use is one pipeline call. Here's the thing, the model never sees the waveform itself. What you record is amplitude over time. At 16,000 samples a second, a 4-second clip is 64,000 floating point numbers. Beautiful to look at, useless to a transformer. It has no notion of loud here, quiet there as a picture. It just sees a flat river of values. So before anything learns anything, that river has to be reshaped. The reshape is the feature extractor's job, and it makes a log-mel spectrogram. Slide a little window across the waveform, ask how much energy is in each frequency band right now, and stack those answers into a heat map. Time across the bottom, pitch up the side, brightness for loudness. Whisper always uses 80 ml bands and pads, or trims the clip to 30 seconds, so every input arrives as the same tidy rectangle. That rectangle is what the encoder actually reads. Now the transformer. The encoder digests the spectrogram into a stack of audio features, a rich summary of what was said. Then a decoder, the exact same machinery we use for text generation, writes the transcript out one token at a time, each new word attending back to that audio summary. It is literally translation, except the source language is sound and the target language is English text. Same attention, same decoding, different input modality. And Whisper is multilingual and multitask by design. The decoder is steered by special tokens at the front of its output. A language token like N, a task token like transcribe or translate, flip transcribe to translate, and the same model gives you English text from Spanish audio. No second model required. Today we keep it simple, English in, English out, transcribe. The piece people forget is timing. The decoder emits words, but words don't carry clocks. So Whisper can also emit timestamp tokens, little markers that say, this chunk of audio ran from 0.4 to 0.9 seconds. Turn those on and you don't just get the sentence, you get the sentence pinned to the waveform, which slice of sound made which word. That's how captions get built, and it's exactly the alignment we're going to draw at the end. One honest caveat before we run it, Whisper hallucinates. On silence, on music, on garbled audio, it will confidently invent fluent text that was never spoken because it was trained to always produce well-formed sentences. On clean speech like our clip, it's superb. On a noisy room, it can drift. Knowing the model is a confident guesser, not a stenographer, is the difference between using it well and trusting it blindly. One file, 2 pages. We load the pipeline, load a sample clip off the hub so there's nothing to download by hand, run it once for the plain transcript, then run it again with timestamps turned on so we can align every word to the waveform. Let's walk it. First, the imports and the device pick. We pull pipeline from transformers and load dataset from datasets. and we check for a GPU. Whisper runs fine on CPU for one short clip, but if CUDA's there, we take it. Because the encoder is the heavy part, we pin the model ID to OpenAI whisperbase.n, the small English-only checkpoint, 74 million parameters, fast and plenty accurate for clean speech. The byte tenant suffix means it skips the language detection step entirely. Next, we build the pipeline. One line, pipeline with task, automatic speech recognition, the model ID, and the device. Under that single call, the library quietly assembles three things: the feature extractor that makes the spectrogram, the model that does the encoding and decoding, and the tokenizer that turns output tokens back into letters. The whole episode 2 through 4 spine hidden behind one constructor. That's the abstraction we keep paying for and keep being grateful for. Then the audio. Rather than ship a WAV file around, we load one sample from a tiny speech dataset on the hub and grab its audio field, which hands us the raw float array plus its sampling rate. We print the sampling rate and the length in seconds so you can see its real numbers. 16 kHz, a few seconds long. This array is the river from the second scene. The pipeline will reshape it for us. Now the payoff line. We call the pipeline on the audio array and print the result. Out comes a dict with one key, text holding the transcript, a leading space, whisper always prefixes 1. And then Hugging Face makes models easy. That's it. Waveform in, sentence out, no preprocessing we had to write. If you only wanted the words, you could stop right here. But we want the alignment, so we run it once more with return timestamps. Word. Now the result carries a chunks list, one entry per word, each with the word text and a timestamp pair. Its start and end in seconds. We loop over those chunks and print each word next to its window. Those 5 start end pairs are exactly the tick marks we'll drop under the waveform, so the picture shows not just what was said, but when. And that's the whole modality. The trick that turned text into ideas back in episode 2 is the same trick that just turned air into text. A feature extractor reshaping raw human signal into clean model input, then a transformer doing what transformers do. One model, one GPU, one clip, the whole way. Next, we stop running single models and start scaling the training itself. Wrapping our loop with accelerate to push throughput across mixed precision and multiple GPUs.